And again, this is a public meeting, so putting this all of this material online publicly. Go ahead, Jamal, if you want to.
Okay, so I'll share my screen. Sorry, there you go. Okay, I think you can make it full screen. All right, I'll get started. So this is work that's ongoing at Bloomberg right now. Nabil Bitar is the main guy I'm working with. The title, as states there, is about offload architecture and we are focusing on a Kubernetes network policy use case. But the general architecture is flexible enough that it could be used for other contexts of networking. The work is based on our effort. I don't know if anybody attended the NetDev presentations. We presented something, an access control scheme called p-tables, and we took p-tables and essentially used it as a Kubernetes data path. And once we did that, we're now moving into making p-tables work as an offload mechanisms as well. So the work is evolving basically towards smart NICs and XPUs, and in our implementation of the offload, we used Calico as the control plane. Our goal is essentially to open source this work eventually. We promised that last time in August when we presented p-tables for the first time, but we are working towards that. To get us started, just to provide some context, I'm going to use some terminology that may have different semantics, slightly different semantics in other circles. So I'm going to define a table as a collection of matches with actions. A rule is a composition of table instances in a pipeline. So if you can think of a P4 pipeline, it would look something along the same lines, but each rule will have its own instance of that pipeline. A policy is a collection of rules. In some circles, it's also known as a rule set. And an ACL is a list of policies. So just so there is to clear any confusion that comes after when I dig deeper into these details. Okay, so our current focus, as I stated earlier, is just the ACLs. Of course, with ACLs you need forwarding, so we're also focusing on forwarding and security isolation. I would list like very high-level requirements here for the data path. We are looking for low latency and low jitter. High throughput, those tend to be motherhood statements, but it's a real need. And the goal is clearly to reduce the host CPU cycles being expended for network. As a result, reduce the total power consumed. Power consumption is also a goal. From a control plane, at the moment, we're using Calico, and we work on a layer 3 setup where entities like BART, for example, for route distribution are important. We have pod and host interface creation and deletion and IP address management and plumbing going on. We are looking for low latency data plane updates, so policies and FIBs in general. Doesn't have to be exactly an L3 table with, let's say, with checksum and TTL decrement, but it has to be able to represent that facility. And we're looking for tens, maybe to hundreds of thousands of updates per second. When pods come up or down, you will end up probably doing more than one table update. So hundreds of, these are updates, they don't specify which tables. The scale we're looking for is tens of ACL policies. Remember, I described ACLs as constituting a list of policies, and policies constituting a list of rules, which constitute instances of pipelines. We're looking for each ACL policy to have a few thousand rules, probably under 5 at the moment, under 3,000 perhaps, and a large number of flows per ACL. So by the ACL, I mean the list of policies, which eventually will create flow caches. And by flow, when I use the term flow here, I mean a 5-tuple flow. Again, thousands to tens of thousands of updates for the ACL side. So at the moment, our focus is just ACLs, but we are going to work on TLS, server load balancing. Our system doesn't have NAT at the moment, but we are looking at NAT in the future. Quality of service, tunneling / overlay, DDoS, IPsec, and further distributions offloaded from this host to the XPU. Here's our current layout of our current ongoing work. I'm going to turn on my laser pointer here so I can highlight things. So this is the host. The top part is the host. You can see at the bottom here we have the XPU, Kubernetes control interfaces with the host still to this date, and the CRI, and we are interfacing with Calico and doing an offload and synchronizing. At the moment, we're using SRIOV as an example, but it could be any of the SIOV or whatever the newer schemes that are out there. But we're offloading ACLs, IP addresses, and FIB control to the XPU. As you can see down here, we synchronize, let's say, the SRIOV interfaces on the host as well as on the XPU. We do local IP management addresses. The external ports, for example, would need to have IP addresses that participate in the Kubernetes cluster. The FIB local control, so how to reach other worker nodes on the cluster, and the ACLs go through TC Flower. That's a view of how things would work into the kernel, and they get offloaded to the ASIC or FPGA that does the Kubernetes offload. So from a control data path separation, this is how it looks. What we're looking for from requirements point of view is this is a canonical representation of a pipeline that could be used or is usable or is used today in Kubernetes for access control. So you can see that there's typically a flow cache where a packet comes in, and if you hit the flow cache, we're looking to increment statistics per flow. So we're interested in statistics per, each flow should have its own stats so we can collect the telemetry afterwards. A packet could be recognized by protocol and port ranges, an LPM table which has source IP and destination IPs they're separate for a good reason. So if you're to think of this as sort of an IP table rule, these will be IP sets. That will be some sort of port ranges and statistics. We're looking for such architecture or a pipeline to be attached to either the ingress and egress. So the offload should support ingress and egress, given that Kubernetes policies have ingress or egress direction. We're looking to add rules to the flow cache on a table miss, where we go through the slightly slower path of these tables here. So this is the general layout. I'll go over the details of how this could be broken down into rules after. So add would miss is a requirement. We are looking to track flows, so we can track sessions basically. The flow cache should have configurable cache auto aging. So when there's no hit for a defined period of time, it gets auto aged. And we're looking for a scheme to describe or define what the cache eviction and replacement algorithm is. LRU is typical, but there could be other approaches that are of interest. Looking for the cache flow to have timestamps for when an entry was created and when it was last hit, so that when we're collecting these flows and their stats from the control plane, we can get a sense of feeling of the utilization of that flow. Ability for the data plane to generate events for the scenario where entries are being created in any of these tables, deleted or updated. and those should be subscribable. I should just be able to subscribe to this source LPM table for entries being added or deleted, or all added and deleted. And the other thing is we're looking for is ability to have actions, one or more actions on a match, right? So the actions we are looking at right now are an accept, which is a drop, a log, a mirror, a redirect, a count, a police, and generic packet editing. Right, so you could use that for things like changing the next hop MAC address, etc. So those are requirements for. How am I doing for time there? I'm sorry, I'm not timing myself. Done. Is that?
You're 15 minutes in. You're great.
Okay. So these are general requirements for the data path. From a control path perspective, control to the data path, which means that we're looking for ways to manage the ACLs, policies, rules, tables, the flow cache, and actions using CRUD semantics. So create, read, update, delete. Ability to do proactive policy programming as opposed to packet driven. Controlled and efficient eviction of ACLs. So if a pod goes down, I want to be able to just send one atomic message to delete all entries that are associated with that pod. The grouping of pods so that you can efficiently reduce the work that's done by the control plane, for example, in sharing the tables and policies. I mentioned this earlier on, subscribing and getting events of choice, useful for debugging and sometimes for just maintaining the state that's in the data plane. We are looking to retrieve telemetry data in an efficient way. So a simple example of that would be just give me all the flows that have seen a hit in the last 1 minute. Don't dump all the flows that haven't seen that a packet in the last minute. Okay, so now I'm going to jump to how flow policies and ACLs are defined. So typically in Kubernetes, you would have, this is not just Kubernetes, but in the industry in general, you'll have some form of intent expression. In Kubernetes could be namespaces or other selectors or key value pairs of some form. And that intent goes through a network context transformation, which creates policies. So if I was to describe a policy, so this is how a policy would look like. You would have tables that are in a pipeline. And the order of evaluation of these tables is from the lowest numbered priority. In other words, this is the higher, this is the most important towards the lowest one. And as soon as we hit a match, we're done. We found a match. Right, and so a match constitutes all of these tables hitting. Right, there's several things to observe here. One is that each table has a unique instance ID, and a table could be shared across rules. In fact, it could be shared across policies, and a table may appear in multiple rules. The same table, like table 1, you can see it multiple times here. And a table could use a different key depending on the context of where it's placed. So for example, you can see that in this column here, the key is a destination IP, but you see table 10, and then you see table 10 in this column using a source IP as a key. Right. Now, what is a policy? Again, policies get attached to what we would call endpoint groups, or this would be pods typically. Could be attached to the egress of one or more pods. So if you have all these pods are all doing DB, they'll be colored in a specific way based on the policy intent. And so the SRIOV or the SIOV or whatever the latest scheme is for efficiently delivering packets directly from the ASIC to the pod will apply here. So you can put as many as meet that intent. And what you end up doing as well is an endpoint policy group could have, like I stated earlier, multiple policies. If I was to go back a little bit here, you can see that policies could be shared. See the red, green, and blue all share policy A. Red and green and blue share policy B. So these policies could be shared across endpoint groups. And the order of iteration is top down. You do not stop when you match on these. You go from policy A to policy B to policy C to policy D. The use case for this is, this could be, if you're looking at ACLs, this could be multi-tier network policies, so set by the security group, and at the bottom line, they could be by the DevOps individual, maybe by the department. Another way to look at this is this could be totally different functions. That could be just the ACLs, that could be just doing load balancing, and the last one could be doing forwarding. But so this architecture plays in a lot of spaces. What you notice here is that there is ordering of these policies, that within the policy, there's ordering of rules. And in fact, even within rules, the tables may have priorities to decide which table entry should match. Am I doing okay on time still?
Yeah, 20 minutes in. So
okay, 20 minutes in. So
I think there's a lot of good content here, so I'd hate to breeze through it too quickly. So yeah, just this is good.
All right. So where we're looking to go next is this is what we think Kubernetes should do, and this is, like I said, this is something we are hoping to achieve. It's not, and there may be multiple ways to achieve this. So you can see is, if I was to go back to the original the current implementation, you see that Kubernetes only talks to the host, right? And if we go to this one, there's multiple things that the less adventurous way is what we're doing is saying Kubernetes is aware of that the network control goes through the XPU. Other things may go through the worker node, which is the host. You could, of course, have broken this down and say, I'm just going to totally move the Kubernetes control to just talk to the XPU and nothing else. One thing we're discussing as something to experiment with is, in fact, we'll remove the CRI totally from here and have the kubelet container runtime instantiation, for example, occur through here and head to its to the worker node. If you go back to this diagram, you see that the offload control happens on the host side, which delivers the messaging for what to be offloaded through socket connection to the XPU. However, if you go down here, you can see that the offload now sits on the XPU, and what we call an onload control sits on the host side. So if a rule is to be, a pod is to be created, one way to look at this is we will send the CRI interface commands through this pipe all the way to some entity here that creates the pod. The one big detail here that I should emphasize is that we are looking for, we don't trust the host at all. That's one approach to look at this is the root of trust sits on the XPU. So everything that has to do with networking cannot be done through the host. The control has to come from the XPU. You notice two trusted applications here. One is the Kubernetes kubelet and associated applications, and then the trusted offload control as well sits here. So the interface, basically, the control comes through Kubernetes, kubelet, etc. here, and Calico would be there, and we interface to it, and we can add rules to the kernel and to the ASIC, as well as when it's necessary, transmit things to the host, right? So pod comes up, it could be totally set up with no interaction from the host. And there are a lot of challenges to be addressed. Sorry, somebody said something.
Jamal, can I ask a question?
Okay.
Of the 2 or 3 different ways that you suggested we modify the Kubernetes, deployment on a node, is there a preferred way that you would want to hint on?
Yeah, so I think the preferred way is to absolutely have nothing on the host. Everything goes through the XPU. I know there's challenges there, right? I'm not sure if the Kubernetes community is ready for things of that sort. Or there may be some surgeries needed in Kubernetes messaging. All right. For example, we're finding a little issues that Kubernetes may depend on a file system that sits here, like on CSFS or things of that sort. But we are we're determined to have it on the XPU. That would be the most ideal solution. Whether
Okay.
that's possible or not, we're not sure.
Yeah, thanks, Jamal. That helps, in finding the right solution.
Yeah, so for the sake of time, I'm just going to go to the last slide here, that our next work is basically TLS offload. And one of the achievements we hope to get out of this is the microservice sidecar, etc., moved out of the host as well into the XPU, right? So you basically get hardware data path socket level entities that sit on the host abstracted on the XPU. Right, with that, I can open up for questions, and I hope Nabil is here as well. He can help answer questions. All right, any questions?
Question on the chat. Can you elaborate on control-driven policy programming?
So maybe the easiest way to explain is through OVS, for example. The way you program the tables is you wait for a packet to show up, then it goes through several layers of abstraction, and then a rule gets added, right? So if you're doing contracting, for example, you wait for the 2 or 3 packets to establish the connection, and then you offload that. Policy-driven is when the Kubernetes policy shows up, we program the hardware at that point. We don't wait for the first packet to show up. It's not driven by, as opposed to packet-driven, which is that makes sense or answer the question? I think we mentioned it here, right?
Yeah, I think in the OVS community, sometimes proactive versus reactive
Right.
is the other term you have there. Is just it's more like a switch where you program the rules and the control plane is the one that's determining the rule set, as opposed to a reactive situation you have in OVS, which is also being very heavily impacted by the type of traffic that you're seeing on the data plane.
I think, I mean, this is the clear way to say it as well, so just to clarify that a little bit, as opposed to having what goes in the fast path to be packet triggered, that's processed in the soft path first, if you will, on the ARM processors, for example, usually on the XPU, and then you program the fast path based on the packets or the first 3 packets. If you're doing a handshake, we do program it open control. When the pod comes up, we want the rules to go directly in the fast path. So that's really the main distinction.
And we have good reasons. Probably this is not the right time to talk about them, but we have very good reasons why we desire that.
Yeah, and Jamal, maybe like, when I go through the slides, maybe it'll become a little bit more clear, I guess.
Okay.
And maybe, I think you had a next steps slide, but all of this work here, is it being developed in the open source, or are you, is it something just for internal usage, or like a, yeah.
I can let Nabil speak to that, but yes, the goal is to make it open source, as this slide shows.
That's the right answer. So I think right now, Dan, we're kind of doing it on our own. I mean, obviously cooperating with some folks, but the intention is to go to open source and work within the open source community. But some early implementations, investigations are still done. We haven't released anything yet.
I think there are a few dragons still to be slaughtered, and then we'll make it open source. There's still the unknowns within Kubernetes, etc., and how things would work. Like one of the issues we mentioned is we're finding a lot of file system dependencies in Kubernetes that are locked in. right? You know, you want to look at something in /sysfs. This doesn't work well for offloads, right? So, and the idea of splitting things into policies, etc., is there's some discoveries still in progress, but we're going to open source it.
Do you see these changes as already having sort of natural places already existing in Kubernetes or Calico or the kernel or whatnot, where these patches get upstreamed, or is this a new project that needs to be created?
So we've Nabil mentioned that, well, as it says here as well, we've been using Calico as the control plane, but ideally this should work with any other CNI or any other implementation, but Calico has been our focus so far. And yes, there's some changes we had to make to Calico, but generally it's clean enough to separate the two. And like I said, one of the earlier after this presentation, one of the first things we did was to offload our P tables as a replacement for the Calico data path, or whatever Calico was trying to do. And now we're taking this work into offloading into the hardware as well. So that interface to Calico hasn't changed.
And Jamal, the Kubernetes changes that we would like for this, we would like to push it into the open source Kubernetes, right?
Right. So I'm wondering if there's any Kubernetes forks online.
I think how to go about that, I think is something to be thought through a bit more, but I could imagine that this could be parsed into different projects, and some of it could be a new project. Like, for example, I mean, when you talk about maybe if you want to abstract a bit the APIs between for the control plane, for example, between the host in either current or future architecture and the XPU, that probably could be abstracted independent of the project. I mean, it could be a project on its own. Now, when you go and say how it will fit within Calico or Kubernetes, those could ride on what exists already as enhancement. But there's something to be thought about a bit more.
Yeah, thanks, Nabil. Then should we go to the next presentation or wait some time?
I think there's no other questions. And we can take more questions at the end of the next presentation. Let's move on to the next one. Yeah.
Okay. Sounds good.
Thank you. This was really good. And so we'll take those slides and we'll post them with the video. So
okay,
we'll have access to them. I assume, right, Jamal? That's okay.
Yeah, Nabil.
Yes, we may do. We may do an iteration on this before we post them, but we could talk about that.
Okay. All right. Yeah, I'll reach out to you. Yeah, whichever version makes sense. Yep.
Oh,
Hi.
Nupur, just 1 second. I'm trying to share.
Oh, okay.
Yeah. Okay, so let me know if you can see it, and then I can.
Yeah, looks good. Can you put it in presentation mode?
I have one screen. Let's see how that goes. Okay. Does that work better?
Yeah.
Okay. Okay, so I'm going to, thanks Jamal and Nabil for kind of highlighting the requirements that you guys have. And I'm hoping that, what we're doing here is matching up to the expectations. So what we are going over is our expectations of what we plan to do here at Intel for, meeting, Bloomberg's and any other customer who's deploying this managed K8's, requirements. So I'm going to go over a few more details based on what requirement that Jamal brought up, which is like why offload more than the flow cache and hardware. And here, hardware, I mean, the main ASIC or FPGA pipeline, not the IPU cores. So, the whole idea is that once we migrate the data plane from host, we don't do an acceleration, we do a complete offload onto the IPU hardware, and the control plane migrates from host to the IPU cores. And internally, as you mentioned, Jamal, that the reason is isolation, and the IPU becomes IPU manages your platform node, and IPU cores becomes your infrastructure complex, or where the control plane is, and then you're hosting your containers or microservices or whatever on the host side. So why do such a thing, such a drastic thing? The rate of programming of millions of or rate of adding millions of connections, that is in some way unsustainable to do it from software. And we know the challenges of that. And again, CPU intensive, and the best way to solve it is let the hardware do the job, instead of coordinating between software and hardware. So in this case, what we really are hoping to demonstrate as a complete data plane offload, where the hardware creates the flow cache based on the policies that you put in the hardware, instead of the software keeping the policies and then just offloading the flow cache. Other reason why do this is to avoid the jitter, which is very well known to reduce the scalability in the data center for how many nodes can provide the service for a given virtualized service, right? So, and this is a very well documented work by Van Jacobson on why jitter is so bad in terms of scalability. So yeah, so we definitely want to avoid or minimize as much as possible that jitter by letting hardware, do that instead of the first packets missing into software. A flow cache, from our viewpoint, is not a true offload. It's just an assist, and we would like to do a true offload, so that there is memory freed up, and the CPU cost, either whether it is the IPU cores or the host, whatever that is freed up completely, and not still tying it and using it for data plane. And there is this last argument is not as strong, because there are ways you could still do the security isolation if you were taking some packets through the IPU cores, but it is yet another attack vector which you would want to avoid, right? So it's good for true isolation between tenant and infrastructure provider, and for future of confidential computing. So those are the few top reasons that we are doing this. Obviously, it's not the easy path, because it requires designing a multiple block ASIC pipeline or FPGA pipeline, and then being able to program it differently, very differently, and but it is for the better of the usability and for all the other reasons that we talked about. Okay, so the next one that I want to talk about is benefits of P4 data plane for K8s. So, I mean, the biggest point here is do the fitting first and fail fast, which means that when you're deploying something on a given node, you would have already compiled your data plane with the architecture or target limitations, so that whether it will fit or not fit for that given node. and you're again avoiding the reactive way of dealing with failures, right? So you're proactively, provisioning and profiling the node, and sending things to the node only if it has the capacity and it has the the ability to do it. And it makes the provisioning of a node into different profiles very easy, which is very true for data centers and telco clouds and everything, where the same node can be used in different profiles, inside the cluster node, edge node, storage node, whatever else. So with this P4 Dataplane, you are able to define different pipelines needed for each of these use cases. It also is key to kind of supporting multiple isolated control planes, as well as the part that Jamal talked about, which is network policy layers. They could be very different, and they can be very different from the profile that node is in. So it gives you the ability to kind of say what network policy layers or tiered policy layers are deployed on this node, and define a different P4 data plane for it. There is more details, about the architecture for this P4 data plane for the IPUs and the DPUs and the NICs that is at the PNA, under the P4 language GitHub. So feel free to look into the details. Here in the picture, I'm trying to showcase what are the possible layers of functionality that can be there deployed in the data plane in the Kubernetes scenario. From top to bottom, you have the network policies, multiple layers of network policies. Then you have the K8s load balancer to kind of pick the backend that is going to provide the service. You want to be stateful, so you let the hardware, create some kind of a flow cache and manage it on its own. And then you have the separated out infrastructure processing layer, which doesn't have to, deal with any of the top layers and, how they're implemented, and basically provide the virtual network, functionalities of routing, tunneling, high availability, forwarding, etc. If there is any question, I'll pause or I'll keep going.
There was a question on the chat about multiple P4 programs. I just answered that P4 OVS supports multiple programs, and there are targets that can support multiple programs, but the compiler would tell you ultimately if it's supportable or not.
Right. Yep. Okay, so very simplistic way of looking at a couple of examples of this method of implementing network functions on the data plane. One that is very relevant to Kubernetes is the stateful load balancer offload. And, looking at it, it is basically, something where you first load balance based on some kind of hash which is not stateful. Then you load balance if you need to based on some exact rule if, you want to send certain traffic certain way because of the hash not doing a really good distribution or whatever reason, or you need to further kind of refine the distribution provided by the hash. And then based on the end node that you're picking, of course, you have to do the NAT updates and all that stuff. And then at the end of it, you want to encache that flow into the flow cache with all the actions that need to be programmed, executed on that flow, so that the subsequent packets can, benefit from it without further having to go through the load balancing and all that stuff block. And this is useful for local and remote load balancing. So, it's a very clean model to kind of capture, once you have gone through the policies for load balancing, you kind of capture it in the hardware flow cache to kind of do that for every packet of the flow. Plus, one other advantage of this is if you remove a particular backend because it's already kind of loaded, doesn't have enough, it's using all of the CPU, cannot handle any more new flows. So you remove that from the hash buckets. That doesn't affect the existing flows that were already going to that particular node, right? So in that sense, it is stateful, make sure existing connections stay as they are, and the new connections are distributed based on the new distribution of the hash buckets. Okay, so this is another example, again, based on some of the stuff that Jamal mentioned, that in these setups, there is multiple layers of network policy that is offloaded onto the hardware. Very similar principle. You go through the policy layers. The first roadblock you hit, the packet is dropped, and you are denying any further progress of that flow. For the rest of the flows, you go and fine tune if they're still allowed based on all the policies. So, going from like something like a broadband filter to a finer tuned filter or something to that extent. And then you encache the result of that policy again in the flow cache with the final decision on this flow. And you encache all the actions as well of, counting, mirror, or logging, or whatever that is in this flow cache. So this helps keep the control plane software to remain as is and not force collapsing of policies, and supports, again, multiple control plane agent to work independently and put the policies in different layers, and keeps the software having to do less of the dealing with flattening and other side effects of it. So that's the second example. Other than that, I just have what are the future work that Nupur and I are working on, which is add more to the Dataplane offloads for the rest of the stuff that is going to make this a complete gates deployment in our data center. So add like, tunneling, crypto tunnels, TLS application tenant security, look into, the best way to kind of offload that on the IPU. Of course, routing, forwarding, all that stuff. And then the microservices offload. And this one, is a little bit more involved work that we have a separate recipe. I believe that is going to come up. Dan, is that something that is scheduled, or we are going to schedule some more?
We have more to schedule for sure, and definitely be interested to hear on Slack or through other other mechanisms to find out where we want to go next with this. I was going to ask you and Nupur the same question of sort of your open source strategy, how you intend to to share this, but yeah, we will we'll be scheduling more of these types of talks, assuming we get good feedback on them. In the next few weeks, we'll start to open up with more topics. We also are trying to get together some sort of event where we can all sort of talk about these types of topics.
Sounds good. So for us, we're going to first finish this whole tiered approach that we have, done for the work that Nupur and I are doing. So this picture is complete. And then we are then going to start the microservices stuff, because there's more of there's more creativity involved in that, and we're taking that as a parallel route. That's about it. So I'm going to hand over to Dan and Nupur.
Nupur, your share. Okay, it's back. I can see it now.
I hope everybody can see it first.
Yep.
So my name is Nupur. I work for Intel IPO team on Kubernetes along with Anjali. And Anjali, thanks so much for going over the details of the Dataplane. I'll today address the CNI components that we are working on to offload the flows to our pipeline. So as an example, CNI, we started our work with Calico. This is just initial prototyping of the work. So here's a very high level of K8s node. The green box here depicts the standard Kubernetes components, except for what you see as IPO agent. This agent implements the API termination, like the add and delete CNI calls, to add a CDQ interface to pods and program the IP addresses and also route in the pod namespace. It is also a receiving endpoint for any Calico Felix policy and service API calls. So all the calls that are being terminated at the agent are stored in a mini database for state maintenance, and then forwarded to IPU manager, which sits on the IPU CPU cores. This manager actually converts every call that comes from agent over gRPC and maps these over the P4 runtime rules to program the table underneath, the matching pipeline underneath. This is our first initial approach. So this is how we want to start before we move on to more splits and to the phase where Jamal mentioned that eventually they would like to see. So this is our initial approach where we are separating out the manager component totally from the host components in a very different secure domain for pushing out rules down to pipeline. And as Anjali and Jamal mentioned, this is not a reactive programming. This is active programming where we pre-configure all the rules as the flows come in, as the APIs come in. So this is the Kubernetes basic flows, and our primary focus has been on the service related flows, which include cluster IP and node pod. So as a part of this, what we have done first is offloaded the entire cluster IP based service implementation to our pipeline, which totally as of today has replaced kubeproxy functionality rules with IPU tables, P4 tables, and programming of rules. We did a demo of something similar at P4 conference recently. Next thing that we are actually working on, or kind of it's also functioning, is the node port implementation for the same service related flow. So this thing includes what is called natting, denatting, load balancing of the connections, then forwarding, and also a little bit of routing to send the information to pod and back again. We maintain our own local web table today. We are updating that from the control plane to make this happen. This is a Kubernetes pipeline. expressed in a very high level P4 logical table view. Each of these blocks is a functional unit, which is in real implementation would expand into multiple tables and multiple matching rules or dynamic rules. Every functional block will be programmed by control plane IPU manager, depending on the policy and the control plane provisioning of flows. For instance, like if a service is created, the pod workload endpoints are added to service pool, and this creates the dynamic load balancing to the replica sets. The initial connection from pod to pod triggers an auto add to the flow cache as shown here. This makes sure that the following subsequent packets of that connections are fast path and treated the same match rules for NAT and policy on a hit. We also have directional counters. So every time the flow add happens and the subsequent packets come in and there's a hit, we increase the flow counters. And this is being used by the control plane for any kind of flow tracing, stats, and counter overview. Next happens is like a BGP-based route distribution that triggers creation of routing tables, which involves sending traffic to different pod CIDR groups and to the interfaces associated with different nodes. So this happens all through control plane programming at various levels. And when the pods get added or removed, they remove certain information from the tables dynamically using P4 runtime. So here's a more detailed view of our control plane. It all starts with a P4 program that implements the logic of the control plane flow. This particular program is compiled today using our PNA compiler. So the compiler generates a couple of artifacts. One is the binary file that's loaded into the hardware. And then there's some user space description files which are created, which give a logical view of the hardware mapping of resources to tables. This particular file is consumed by what is called the IPU manager, so that it has an idea of what table structures it needs to program. And when the API calls come in from the control plane shown in orange up there, those API calls and the data structures are sent over a gRPC connection to using a P4 client to a P4 server, where the mapping of these individual protobufs data structures are done to the JSON table attributes, match action table attributes, to program the tables. We have what is called a TDI layer. TDI layer exposes C and C++ API interfaces for programming the table interfaces. So using these TDIs, the hardware is programmed. So this is how we are stitching today our API-based flows to our P4 runtime and eventually setting up rows in the hardware pipeline. That's pretty much, I just wanted to describe what we have implemented so far. So so far, yeah. So
Can
far
you go back to the P4 program so people can
oh, okay.
look at it? There's a lot there, and so after this, if you can send me this, we'll post that P4 slide. Oh,
yeah.
We can see your chat. I guess it's just the same meeting that we're in.
Oh,
but,
sorry.
Yeah.
So.
Oh, there's the chat. Is there any questions on this? So thank you. That was really great. We had some questions on the chat. I won't repeat them here. I think that they make it into the recording. Some questions on CDQ, some questions on the more discussion on the reactive and proactive And then there's a link in the chat on PSA for tenants, which looks really interesting. So I'll make sure to get that on the Slack channel. There's a question that just came up for this implementation. Has there been used the P4 OVS fork that exists in the GitHub? Nooper?
The P4 OVS that exists in GitHub today does not have our pipeline P4 rules. I think those will be published separately out. Anjali, I think, is writing a recipe book based on that. We'll be publishing some sections of PNA program out to different users, to community. But there is definitely a video that we released to the community on our P4 Euro work, where we demonstrate at least the service level flows end to end.
Okay, but you're writing PNA programs that eventually will run on the P4 OVS that's on the GitHub, right?
Right. Yeah, that's the intention. So whatever components have been so far pushed up and open sourced, like P4 OVS and the TDI layer that is available today, we are using exactly those components to do our programming of pipeline.
So the P4OVS is used to actually in your setup that you just shown in your slide deck, but it's not the upstream one. It's an internal one.
P4OVS, yeah. So P4OVS, what's been upstreamed is pretty much the same code that we are using internally as well. Only difference is that there is some new features which are being added to existing P4 functionality, which will be upstreamed pretty soon, but that's the only difference.
Open sourced, really. The version on the IPDK, the open source version, is intended to be developed in the open source. We're just waiting for our our infrastructure to get finished, and then that open source version will be the same version we use internally. And then the upstreaming process back into OVS is I think longer term. I think we posted to the mailing list and got some feedback, and we intend to break up the patch set so that it's a little bit easier to upstream back into OVS. But the intention is to use that IPDK version as sort of a temporary open source development place, so that people can see the same code that we're working on and we're running these types of P4 programs on.
Thank you.
Thank you. We got through all three presentations. That's amazing. With only 2 extra minutes. Thank you very much. I will post all of these videos. I'm going to stop the recording, and we will absolutely have follow-ups if there are more questions.